divided by the temperature at the spot. I, SI minus summation M dot E SE plus entropy generation. A perfect turbine operating under steady state, steady flow conditions would have no heat transfer and would generate no entropy. So, and for this turbine that's vanished, right, we'd have one inlet and one outlet. And so we would have M dot I SI equals M dot E SE, but it's the same mass flow rate. So SI equals SE. So we could know SE, which equals SI, for the exit of a perfect turbine. And so we could go to ref props and we could say for the same pressure at the exit, 150, and the entropy at the inlet, our perfect enthalpy would be 1261.2. Rather than 1289.4, rather than, what was the other numbers? 1363.
Question.
Right, and so there's the game to play. What number did it come out to be? 72? So isotopic efficiency about 72% for this turbine. Questions, comments, points of clarification? Everybody all right? All right, all right. And the second problem is just as easy, right? Let's see, different steam inlet conditions. So we had steam flow rate of 30,000 pounds an hour, 600 psig, 850 degrees Fahrenheit in. Exit conditions are 90 degrees Fahrenheit, 1.43 inches of mercury absolute out. Let me say, I didn't just change the units on you here to be mean and make you do unit conversions. This is the common way to describe exhaust pressure for a condensing turbine. Okay, that this would be the most common way of describing it, either in inches or centimeters, millimeters of mercury, right? So that's the most common way, because the pressure sensors for these below atmospheric pressures, they get expensive and exotic. And so what we wind up doing is taking a glass tube that is 32 inches long, okay, and turn it upside down, okay, with the opening at the top, pouring liquid mercury in it, really and truly, right? You'll pour liquid mercury in this tube, so that it's full all the way to the top, and then we got a little bowl, like this thing, right? Okay, it's pretty deep. Okay, it'd be hard to carry, filled with liquid mercury, but with liquid mercury in it. So we take this tube, and you put your thumb over the top end. Okay, full. It's totally full of mercury. Okay, when you put your thumb over it, some drops come off, so you want to stand over this, but they're going to splash and go all of a sudden. It's going to make a mess, and it's toxic, and you don't want that stuff around you. But that's what you do. Okay, put your thumb over the top thing, turn it over, and then put your hand and the tube under the surface of the mercury. Okay, and stand it up. And so that mercury, remember what we did over in the classroom over there with water? Doing exactly the same thing, except mercury's a little bit heavier than water, right? So instead of taking 30 feet to break apart, to create a perfect vacuum, it takes 30 inches to make a perfect vacuum with mercury. And so what we wind up doing is, instead of having this thing sitting here measuring atmospheric pressure, we allow the glass tube to be filled with mercury, okay, and we connect it to the turbine exhaust. And so we're going to measure how high the mercury comes away from the end of the tube by pulling against, not a perfect vacuum, but the same kind of thing. So we'll use a mercury manometer, mercury field manometer, to measure these turbine exhausts. And so I wasn't just being mean. I was being mean, yeah, but not just being mean. This would be the normal way of doing things out in the world, and this would be the normal way of doing things out in the world. So you'd get those values and have to mess around with them, right? Electrical power generation of 3.4 megawatts, and a possible generator efficiency of 95%. So what'd you do? How did you do with this? What kinds of things go on? First thing I did, you don't have to convert. If you're using ref props, you could just change the units in ref props, but I decided I wanted to convert that. So what in the world did I get conversion to? I got minus 14 PSIG, if 14.7. So a 0.7 pound force per inch squared absolute is the pressure I got for this. So just because I wanted to stay all in the same unit, so that equals 0.7 pound force inch squared absolute. Right. And so when you do 600 and 850, what happens there? So let's do 600 and 850, and you wind up superheated. So that's great. That's great. If you do 0.7 and 90. So something's funny there, right? Did I do something wrong?
Gauge, right?
Oh, gauge, that's right. Very good.
It's just testing the time.
Minus 14, and it goes, what, right? Or that's what it does with me. I don't know what it does with you guys, right? It goes, hey, what's going on, right? Something's not right. Can't handle. Well, this one can handle that. All right. So, was this the path you guys took to solve this problem? Yeah. All right. Well, let's see. So if you take this path to solve this problem, then you got an enthalpy, a real enthalpy coming out of the turbine of 1101. Let's take one quick look at that. Now look at that. If you put in a quality, if I use minus 14 and a quality of 1, the saturation temperature is 89.859. As my therapist says, how does that make you feel? How accurate are our thermometers? Well, if you're at NIST in Gaithersburg, Maryland, and you're working with the absolute calibrated Krypton thermometer, okay, it might be accurate to 2 decimal places. But if you're working with your thermometer, or a thermometer at Eastman, or at Domtar, on a turbine exhaust, wonder how precise and accurate that thermometer is going to be. I think you got a good chance at having saturated steam here at the exit of this turbine. What does that mean for us?
It's not
Say again?
It's quality, not 100%.
But do we know the quality of the steam coming out of that turbine? I'm skeptical that we know the quality of the steam. Very, very, very skeptical that we know the quality of the steam coming out of that turbine. I doubt we do know the quality of the steam. The only way we could know the quality of the steam coming out of the turbine is with this information, would be if it truly was 90 and slightly superheated, or if it was 89.59 and saturated vapor, dry saturated vapor. But saturated mixture, 50% quality, is going to have exactly the same pressure and temperature. Saturated mixture and 2% quality is going to have exactly the same pressure and temperature. And 2% quality is going to have slightly different enthalpy. It's going to have an enthalpy that is 100 instead of, or 200 instead of 1,000, which would just turn your answer totally on its head. Okay? So, if you went this route to solve this problem, you'd be wrong. Okay? You'd just flat out be wrong to go that route. So what should you do? Well, probably what you did. So let's see what we do. Right? Guys, I'm sure did this. So game that you need to play. Same old game, right? We're going to do conservation of mass, and conservation of mass is going to say m dot I is equal to m dot E is equal to m dot. Conservation of energy is going to, same song and dance we just did 4 minutes ago, right? We're going to find that the power of the turbine is equal to the mass flow rate entering the turbine times the enthalpy entering minus the enthalpy exiting. Trouble that we have is I don't think we know the enthalpy exiting. I don't think we know that. I don't think we've got enough information to tell us the enthalpy exiting the turbine. But electrical power generation of 3.4 megawatts. You know what? This power of the turbine, the power of the shaft, right, is equal to the electrical power, the power coming out of the generator, conditioned by generator efficiency. Right? So if I had an estimate, an understanding, a measurement of generator efficiency, and if I knew electrical power generation, then I could know shaft power. If I know steam flow rate, And if I know the inlet conditions, then I can solve for exit enthalpy. Yes, Nathaniel?
Why would we need to solve for the exit enthalpy if we already know the power out, and then we just can do the isotropic to find the isotropic enthalpy out?
If that's all you want to do, perfect. Yeah, no problem, right? If that's all you want to do, great. However, I think I asked another question. Determine the cooling required. I think we're going to need that for that part of the puzzle. And most often, if you're dealing with turbines, condensing turbines, you actually do want to know what the exit quality is, because that gives you an understanding of how wet the steam is coming out of the turbine, and whether you should be concerned about droplet impingement on the last set of blades causing erosion and maintenance trouble and efficiency trouble. So good question. Yeah, good. All good points. All good questions. So I'd wind up solving for enthalpy at the exit of the turbine. And I would also play the game of isentropic efficiency is actual power over isentropic power. Actual power is 3,400, just what Mathan says, right? 3,400 over generator efficiency times, or in the denominator, times mass flow rate, enthalpy entering, minus enthalpy exiting an isentropic turbine. So let me do this. Instead of putting 3,400 there, let's say W dot ELE, right, electrical power generation. Now, why in the world am I doing this? Is this one of those physics things where we're just giving you a problem that forces you to do algebra and work things around? No, this is reality. In the real world, we've got, I have no idea what's at Domtar. I'll bet you there's one of these exactly like this at Domtar. Bet we've got a condenser pressure that's near these conditions. And I guarantee you, it's saturated coming out of that turbine. When we were at John Sevier, that turbine's discharging saturated steam. It's got a quality less than 1, guaranteed. And not guaranteed, you see it. You see it right there on the screen. So at John Sevier, their steam turbine, the big steam turbine on the condenser section. When you look at it, if you try to do an efficiency analysis on it by just taking the measurements here, you get meaningless information. You get really low efficiency, okay? And it's incorrect. It's just wrong. You go search for something. Why is the efficiency so low? You go searching for something, you don't find anything. Because there's nothing wrong with it, right? Because you're the one wrong, right? Your analysis is wrong. So what do? You go to the electrical generator and you measure electrical power output. That's what we really do in the field, okay? At Domtar, we would walk up to the number 3 turbine generator and we'd go to the electrical bus and we would measure electrical power out of that turbine generator, and that would give us this value. Then we would either estimate from manufacturer's data or go and measure it. You can measure generator efficiency. At least you can get a really good estimate of it by heat loss, the thermal energy leaving the cooling avenues of the generator. So you get an estimate of generator efficiency. We've got to have a steam flow meter or a condensate flow meter. Very often, instead of having a flow meter here, introducing pressure drop that hurts the turbine's performance, we'll measure the flow rate of the condensate, where the pressure drop of the flow meter does not hurt our performance noticeably, even measurably. There, one way or the other, we get mass flow rate. We would measure the inlet steam conditions, and we would measure the outlet pressure. Thus, the reason I'm talking about mercury manometers and all that other stuff, right? Because it's important to get that pressure right, to understand what it is, to have an accurate measurement on pressure, and we have ways of doing that. So there would give us that. And so this would be the way you would get isentropic efficiency of most real-world condensing steam turbines. Questions or comments? Yes, Nathaniel?
You got the exiting enthalpy, the
Huh.
real exiting.
What numbers did I get? Did I do this problem? I did this problem. I got numbers like, make sure I'm looking at the right stuff, seeing the right thing. Yeah, this looks right. So I got isentropic efficiency of 76.4%. I got an exit enthalpy of, I'm trying to see what quality is. Isentropic quality was 80%, 81%. Quality of the steam for a perfect turbine was 81%. The